without wasting much time, let's start with the concept of shadowing. So here is a program in Rust. As you can see, I'm using X for 10 with size with type U32 and X with hello string. And I'm trying to print X here. So like you have three choices. First one, will it print 10? Second one, will it print hello string? And the third one, will it print, will it cause an error? So can anyone guess and write it in the chat and we will discuss over it. And also note that we are not using mute keyword here to make X mutable. So it's immutable throughout the execution.
Well, I'll guess it should print hello, but I'm not sure.
Yeah, okay. Yeah, so at first glance, this may seem odd, where why are there two variables with the same name and different type? Shouldn't the Rust type system prevent this from occurring? So this is what called shadowing. So the Rust compiler will take the latest value assigned to the variable name, in this case from the number 10 to hello, and utilizes that until either the scope ends or it is shadowed again. So shadowing is not the same as declaring a variable mutable with mute, as it remains immutable after being shadowed, and the let keyword must be used to shadow a variable. So let's first run this program. Here you can see it's printing hello as as we discussed. But if I remove this let keyword and just simply assign it to hello, and then it says that it was expecting U32 type but found and str. So in shadowing, we can replace the value using let. So shadowing with let, we assign the variable to a new type and value, redefining it altogether. So that was the concept. And let's move to the another one, that is alternative data types. So in our previous workshop, we have seen some primitive data types that can form basis for more complex data types. So these data types are complex, but are provided when certain primitives are not able to accommodate some special scenarios. So we will see two scenarios. So first one is large numbers, and the second one is deterministic data types, that is floating point numbers. So in large numbers, when we want to represent very large numbers such as hash or even an electric derived public or private keys, it often requires us up to 256 bits of data. However, the Rust standard library supplies data type up to only U128 or 128 bit long numbers. So an alternative we can derive from this is we can use existing data structure such as string. However, this could be costly as well as cumbersome later when we try to read it. So there are some substrate libraries such as SP core. There we get one method or data type which is U256. It is not a native library of Rust. It's external library, so you need to install it or uh, i- uh, or use it in your cargo.toml as dependency. So here I have mentioned the version, and after you mention this library with its version, you need to run command cargo check or cargo build. So it will automatically download and compile the library into your project. So here I can use it directly since I have already built SP code. So let's take a look into this. So like this provides primitive for dealing with these large numbers, and this is U256. So let's try large number. There's a method which is called from decimal string, and here you can uh, store any large number. For example, this is random, and we will use unwrap to print this large number here. Mm. And also, since I yeah, so this is how we use uh, this notation is used to print these number or variables inside a string or print statements. So here large number, and let's run it. So here you can see this is a very large number which won't be accommodated in our regular U128 type. Let's try this. Yeah, okay. So here you can see the error that integer literal is too large. So this is very similar to big int or long in C++ and Python. And because Rust cannot just simply store an entire 256-bit number in one variable, this is a custom data type which was created. And this particular type, that is U256, actually stores the data in four block of U64. So it's kind of like U64, 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 and U64. So this data is broken down into these four blocks and stored. And the second alternate data type will be deterministic data types, for example, floating point numbers. So many times you must have seen these error or these situations where you multiply some floating point, for example, this with um, anything for simplicity, 3. And when you try to print this value, most of the cases are like correct when you get 5 decimal and 3, but there are some cases when you get this and 1 at the end. So this is inaccuracy in non-deterministic data type, basically floating point numbers. So because as different architecture we calculate the different end result. For example, a 32-bit system will calculate a floating point number differently from a 64-bit system. So while this inaccuracy is not a terrible thing, but in the case of dealing with things such as balances in a blockchain or floating point rounding errors that could easily result in different nodes calculating different balances and potentially never reaching a consensus. So for this reason, the notion of floating point primitives such as F32 or F64 cannot and should not be used in context of blockchain runtime. So there is a library, SP arithmetic, which gives us fixed point arithmetic functions like these you can see. We'll be using 128 for an example. Let's name the variable as fixed point, and to use this, you just write and double colon. There's a function from listener. Here you can see there are different function, but for this example, we will be using from rational, and A is 25, B is 10. So this is basically 2.5. and we will print this variable here. But for that, we need to use, because it's a complex data type. Then we will run, and here you can see 2.5. So it's a deterministic data type, and it will not have those inaccuracy in it. And the next one is traits. I have used traits in our previous workshop, but we will be diving into more advanced form here. So as I mentioned before, that there is no genuine concept of object-oriented style inheritance in Rust. So traits introduce the notion of defining shared behavior for data structures. So let's see how we define a trait. Yeah. So defining a trait utilizes the trait keyword. First, we define its visibility as public in trait, and followed by the name of the trait. For example, transferable. Now, this function defines a trait transferable. We will define a method signature, which is called transfer, mm, which nav needs of transferring to who. And amount of strength I32. This returns I32. So this signature is a blueprint for what we expect from any type that implements transferable as a trait. As implied by the name, this trait would allow a type to send currency from the caller to who, this who. And the use of this trait would allow for a particular type to now possess these methods in order to achieve this functionality. So there's a difference between this self and this self. This self with a small s refers to an already instantiated instance of that type, whereas this self refers to simply that type. So the use of this self here allows for this trait to look for the specific type being implemented when it comes to the who should receive the currency. And to explain this more, I can do one more thing. That is, let's okay. So first, let's define the implementation and all. Then I will explain the difference between these self in detail. Yes. So this is how we define our own trait, but we also have some Rust native traits such as debug, partial equal, and clone. So let me introduce partial equal here. So for that, and this will be implemented in a struct. Yes. So this line, there's a declaration of derive. So this is what called a procedural macros, which creates a sort of auto implementation for a set of compatible traits. So between the parentheses, any trait compatible with this macro along with the struct field within can be implemented. So this partial uh, equal give us functionality to use equality operator. This one, double equal. So let's use it. In our main function, we will define two entities. this is similar to comparing two different string in our Rust. Let's change it to one. Yeah. So if we run our program, it will tell us that these entities are not equal. So it will return false. But if we remove this line, it will throw an error because we do not uh, have a function to directly compare these two strings. So here it says binary operation double equal cannot be applied to the type entity. So for these functionality, we define trait and macros and all these things. So this was the Rust native trait. Let's work on our transferable. So for that, we will define our own struct, that is account, which have public ID I32, balance, and is legit. If the account is legit or not, this is Boolean. Then we will write implementation for our transferable trade using IMPL for account struct. Yeah. Okay. So if we leave it as it without uh, implementing the transfer method signature, it will throw an error. So here it says missing transfer in implementation. So whenever you define a trait, it it contains some method signature. If you miss any of the method signature in your implementation, you will get this error. So let's implement uh, implement our transfer function. For transferring, it will give self balance minus 100, and it will add the amount to who balance and then just return the self balance. So yeah, now if we compile, it will compile. So because we implemented transferable with this type, now any instance of the account struct can utilize this transfer function or method and ensure shared behavior. So let's try to create two accounts. Which have ID 1 and the second one string up 200 balance and is legit true. So now semicolon. So now to use this transfer function, we can simply call this method on an account type. Let's say Chris. Let's transfer from Chris's balance to this account, and the amount is, let's say, 50. Print. Mm, Irritable. Yeah. So as you can see, after calling this transfer function, there's a change in balance of both accounts. Now, uh, so in fact, any type that implements transferable can now transfer funds. So as long as it's implemented correctly as per the method and the trade signature. So to illustrate this, let us add another method signature to transferable, which will drain all the funds from an account. First, we need to define here our method signature. And if we define a method signature, we have to implement it, else it will not compile. So let's implement it first. Very simple logic. Just change the balance to 0 and return true. Now let's test our drain function. And print the final dummies again. Yeah, okay. So it was previously 50 and 250, but now since the all the funds are drained from others account, now it's 0 and it's 50. So there's a one thing to note that drain funds return a bool for simplicity, but we should use result. Uh, this result t and error. So this would be more appropriate here, along with the more robust checking on if the user is allowed to drain their funds on what. Yeah. So there's one more concept of trade parameters and bounds. Since we use trades, the common use of trades is their use as bounds in function, which can then be used to define parameters that abide by these bounds. So with generic types, this becomes possible and gives very reusable code. So for this scenario, we add one more additional method to the transferable trade, that is legit, which verifies that the legitimacy of a particular entity or account could be, it could be account, smart contract, or any type. With generic type we can do this for any variable. So first define uh, another function signature, which is legit. This takes self and return true. Now we need to implement the implementation for is legit function. This contains the logic to check uh, if self balance is not zero. That is, we have some non-zero balance or positive balance. This is the implementation. Now we will define one more function to use this implementation and check if any account is legit or not. For that, there are two types of implementation how we can define this function. First one is very basic. mm, Function verify entity. So this function parameter entity is saying something very particular here. Any type which implements transferable as a trait is a valid parameter. If we were to define another type, let's say smart contract, that implemented transferable, then that would also be a completely valid. And if we want to convert this into more generic trade bound syntax, which allows for a better view of generic at work, we will do this by using angular bracket T, then transferable and the parameter. Yeah. So let's complete this function. If entity is legit, good. So to call a function like this would be a very interesting, as we would need to specify which type. So as long as it abides by the trade bound transferable. Since we will be discussing over T later, so let's use this function. Yeah. So here account goes in the angled bracket as it's a type key that implements transferable. And we also have another method to call verify entity, that is simply call it with and account account variable, and this will work. Since we already drained all the funds from Adit's account, so the balance is zero. And if balance is zero, that means the account is not legit, and it will just print the entity is not legit. So that's how we use trade. This transferable was our customary trade, and we can define behavior or the methods we want to use it, just like the native REST traits we have, uh, debug, clone, all those. So this is very similar. And the next we will be next topic is generic code. In our last example, since we used T, that is generic type, we will be discussing on why we need generic code and how we use it. So let's assume that I wish to have a simple function that is meant to square two numbers as we had previously done. Let's write the function which returns I32 type and simple logic x multiplied by x. Yeah, so this code is acceptable. However, there is a problem. What if other number types must be compared? After all, same function could apply to F32, F64, U32, and so on. So generics remove this redundancy by defining an abstract type, usually referred as key, which allows the function to be compatible with many types. So to convert this square function into a generic one, the sentence that we apply will be as first we define here t generic type, and uh, and this x will be of form t, and the return type will also be t. So the most glaring difference is the introduction of this angled bracket t here. So this syntax proceeds with the parameter list, defining what the generic is called and what properties it should entail regarding traits. So the type T in this context quite literally means any type. So meaning the function can now be called uh, as using I32 or F32, anything. So let's try this. Yeah. Okay. So uh, we will get one error here that we cannot multiply T by T. This is because this is possible for any number. So not all type can utilize the multiply operator. For example, if you use string, this function would panic as it is impossible to compare strings directly this way. So this code should not work as the compiler is unsure what to expect since it can expect any type. So we cannot use string here. So we need to define the behavior of and restrict the behavior of T here. So for that, we will use mul trait that ensures that a type that can be multiplied. So we will be using only those type that can be multiplied using multiply operator. So for that, we need to change this syntax slightly, like T using mul trait and the associated type, that is output. And for using annual, you have to use std ops mul to import this here. Now, you can see that this will compile. Yeah. So we have implemented this correctly. And now to use this for any type, we will simply we can simply call this a square function in our main. For example, squared let's use that for I32. Yeah. So we can use this function now for different data type. Uh, as this is I32, we can change this to U32 and see if it works. Yes. And we can change it to even float, but for that you need to add decimal and it works. So this is how you define a generic type and convert a function for any generic type, and also using this trait to ensure that whatever the parameter we pass in this function is compatible with the operation. So let's define one more struct here. That is point, geometric point. And this will have two values, x and y. Yeah. So so multiple generics may be used because the type of x must differ from the type of y. If we want to differ y from x, we can use u as well. So so generic labels usually follow this convention, but in theory, uh, can be named anything. So here you can change t to u. That means x can be of int and y can be of string. Let's test it in our main function. Let's define point. Now there's one incomplete implementation in this code which will cause an error, and I want you guys to find what should I fix. Let's first run this code. Okay, I am not printing print here. Sorry, print and then yeah. So I'm trying to print it, but it will throw an error. So can anyone guess or try why this is not working? Yeah.
I think Point needs to implement something that is like big printable, basically.
Yeah. Yeah, you are correct. So like this struct should have a function or functionality which will help us to print its value. This is basically macros that we defined in our previous example. So this will be like derive and debug. So like in other programming language, we use print statement and all those kind of stuff to debug our code. So here, if you want to debug some complex data type, for example, struct, string, vectors, we use debug here. So since we have implemented debug, it should print the value now. Yeah, so here you can see the struct if it is printed. So this so yeah, so this is how we use generic code. And uh, the next topic is lifetimes in Rust. Yeah, Mahmoud.
May I ask a question? The first function square. I don't understand the copy. Like I don't see it imported, and despite that, it compiled what it is like. Uh,
Yeah, yeah. Okay, so as you can see here as well, so for using any variable uh in our function, we need to copy or duplicate the object and is so that we can modify it or do some operations on that parameter. So we use copy. So this is similar to clone. If I want to copy this point or make a deep copy of this point, I will use here clone. As you can see, we have copy function as well. So basically, if we use copy here, we will be able to change the value of x or do any operation on x. So it's like uh basically and here we use many times and vector. So this is passing by reference. So this is very similar to that. And if you want to change or modify this value of x, we need to use copy. Mm, Did I solve your question?
uh, I'm a bit confused also because you could actually use it without importing it. Like if you know what I mean, like no way uses and check it.
Um, Basically, since we are using uh generic trade here, but like if I do it to the initial step, yeah, this one, and now call the square function. So okay, I this will work, but if I use generic term here, like the generic function that I wrote before, it need to use copy because we are using associated output type as well. So like this is like moving this type declaration within the trade as an output type. So basically, if you see the MUL implementation, okay, and go back. Let me just rewrite this. And here you can see that this is also a trade, annual trade, which have uh, output as a associated type. So basically, if I use any if I use this trait within a function, it it cannot just use the variable or the parameter that I passed directly for its operation. It need to copy the object first and do the duplication and then proceed with the operation on that duplicated object and then return the output type here. So uh, that's why we are using copy.
Yeah, got it. Thank you. Makes sense.
Yeah, because we cannot directly just use x in this trait, so that's the reason. Yeah, so next topic is lifetimes. So lifetimes are also generic and are used to validate differences. So for example, if I define main function here, this is uh, this is lifetime A, and let's define a variable and another scope. So this will be lifetime B. Let's define X in this scope and Y equals X. And if we later try to print Y, this will throw an error that X does not live long enough. So, so in essence, lifetime is defined by the scope in which a particular reference is deemed valid. So, in other words, it uses the borrow checker to ensure that the dangling pointers do not occur. And this is the perfect example of dangling pointers. So, if we just run the compiler, it will tell the entire story of why this cannot work. So as here you can see, binding X declared here, and the borrowed value was here when we assigned Y to X, and then X was dropped here after this curly bracket when the scope was closed, and then we are later uh, borrowing here to use Y. So this is a dangling pointer, and this is defined by lifetime how we cannot use uh, this structure. So we also, one thing to notice here is that we have not explicitly defined lifetimes as they are implicitly done for us. So we just mark the lifetime here in comment. So there's also annotation. As mentioned, these are generic type. So they also follow the convention of an apostrophe A followed by the letter of going from A onwards. So like if you want to annotate a function with explicit lifetime, we can use apostrophe A, for example. Let's define a function that is bad lifetime with A. This is very similar how we define generic. It was T here, and this will give us return of ITP2. Now here, right, is equal to let's say 19, and then return 1. So here also we can see that lifetime is lifetime A defined here. So now we can define lifetime explicitly using apostrophe A, and binding was done here. Then the value was borrowed, and type annotation request that is borrowed for A, and this is dropped the after these functions get over, like it's at the end of the function. So uh, so this underscore X does not live long enough. So this is example of bad lifetime. To fix this, we need to change few things. For example, we-
and then return x. This should work.
Let's call this in our main function as well. Yes, so here you can see we fixed the lifetime of A, and even if it now when like uh so as the function this should work, and like underscore x do not live enough, and uh like in the previous example, because it was deallocated from memory, and the y then pointed to the deallocated memory. So this is solved in this example, and the previous example was for the dangling pointer. So for this one, we must ensure that underscore x is a reference that has the same lifetime as y, as well as the function itself. So we defined a here and a here. So both the function and the underscore a have the same lifetime. So this works. And also there's example of and str. So this is known as static lifetimes. It's a unique lifetime that which explicitly defines a reference as something that can live for entirety of a program. So basically this stay literal as they are stored in the program's binary. It makes them always available. Yeah, that was yeah. Uh, yes, so that was it for lifetime in Rust. And the last concept is visibility. So for visibility, I first need to explain the difference between the crate and modules. So for example, uh, this this is my main.rs. This is our this is our crate. Let's name it as my crate, and we can define a module here using mod keyword. Here goes the content, and we can also define some modules. For example, module B, this contains another module. Mhm. So let's define the definition. Yeah, so that's how you define module, and uh this file is a trait. So anything in this file is a trait, and this this scope is a particular module. So the main difference is that the trait is the largest unit of compilation in this, and it is essentially a project or a library. And you can create a trait using this command, cargo move, like we created our uh, course module, course trait in our previous workshop. So you can create any new trait using cargo new and the name. So that's how you create a trait, and a trait can be compiled into either a binary executable or a library. So and the module is a way to organize code within a trait. So it's like a namespace or a container for items, functions, stubs, etc. And the modules can be nested inside other module, and you can define the modules using mod keywords. So the difference is that trait can contain multiple modules inside it, but a module is always part of a trait. and thread are compiled separately, while modules are compiled as a part of their containing threads. So you can have dependencies between threads, but modules within a thread are inherently connected. So there are two type of visibilities. First is private and the second one is public. Let's let's define a module, which is my module. This have a function. Let's name it private function because items are only accessible within same module and its submodule, and it's the default one. So we don't need any keyword to define the visibility. This is private one, and we will simply print this is private to my module. And let's define another visibility here, that is pub, that is for public. Here we will print this is public and in Bitcoin clone anywhere. And to call this function private function, we cannot call this outside of this module. But since this function is public and this function can call this private function, we will use this private function here. And for testing, so and this right of main function. Now, to call any function from a module, we have this syntax. First, we write the module name. Then let's call public function here and run the run the program using cargo run. Here you can see it printed this is public and can be called from anywhere. So public function, this line is executed, and the next line, private function. So this also get executed here because this function can call this function whether it's private or public because it's in the same module. But if I try to call this function from our main module, we do not have suggestion as well. So let's just try. If we call this private function, it will throw error that it's a private function, it cannot be called. So we have a few advanced visibility modifiers as well. Let's see the. Let's define a nested module. This is outer part, and we have create and the inner module. This is of type in path, and in case of path, we will define the outer module from this crate. So we can say this is semi-private function. And we have one more type, that is pub super.
This function is visible in the outer module.
So to use inner function, we define another function which will call the super visible function in semi-private functions. And also we will try to call the private function. No, we don't have. We can define, but in
Yes, yes. Mm. So,
yes, as we can see that when we call pub crate, so this basically makes an item visible within the entire crate. And when we call pub super, this makes item visible in the parent module. And there's one more in path. So this is path. And if we specify a path, this makes item visible within that specific path. So here, when we call create visible function, this function is visible throughout the crate. So I can call it in the main function. Let's see. Let's test other functions as well. For example, use inner functions that we defined earlier. So inner functions have two super visible and semi-private functions. So this is visible in outer module, but since we are calling this public function within that outer module, we can call it. But let's try to directly call this using inside our main function.
super visible function and value.
So so for that, this will say that it's a private function. It can't be called outside this outer module. what if we try to call semi-private? So this also gives an error because this semi-private function is defined for the path that is outer module. So this is visible for uh, only the function that are defined inside this module. And here, this can use semi-private function. But if we try to use private function which do not have any keyword or any specific visibility, that is, it's a private function for only the inner module, it should give the compilation error. As you can see, it says private function. So uh, these so this is how we define visibility rules. So yeah, okay. Like there are only two types of rules, that is private and public. But if we want to define public, uh, like semi-private function and super and path, we can use these keywords for the definitions. And this was also a doubt from Chris, I guess, in the last workshop, how we use pub and private. So that's it from my side. I know this was a bit more theoretical and uh,
This is being recorded, so if
okay.
there's anything that you missed, Julia will provide a link.
Also, I have updated the solution for our challenge. This one, it's a very flexible challenge that you can use anything you want, any creativity, anything. So my solution is here, and I have posted this in the same just repo on GitHub. So this is very basic. First, I am using blockchain module, importing it. This was provided, and then here we need to use primitive data type literal operators. So this is basically level experience using U8 F32, and then struct enum. Then here I am using trait for debug, clone, copy, and then constants for level and experience. This is the implementation for the pet. And if you want to create new pet, you can define here the species, the name, and this is method for calculating initial experience. This also contains scope and shadowing concept. Then we have type and casting. So here and this one as well. Then the conversion part. Then using display for our species struct and triform into expression. This is the implementation of crypto pet game. If else block, loop, while, and the matching. Then while, let, closures, high order functions, diverging functions, and the main. Also, there are some tests, and one test is failing in this, and I want you guys to find out the bug in that, why it's failing. For example, if I run this test, two tests passed, one failed. So it's a further challenge or task to find why that test is failing. And yes, the code is complete for for our uh, for our challenge. This one, so you can reference it. And also, if you have tried this and did something new or creative, you can share your solution with us. Yeah. Thank you.
Thank
Thank you so much.
Well,
Thank you,
if
Chris, for your
if
time.
there's nothing else, I hope everybody has a lovely rest of the day.
Have a nice day.
Have a nice day. Yeah, basically. Bye, guys. See ya.